Okay, so we're going to be going over Calculus 2.8, which I don't have my book, so I'm gonna be doing this off my head. And I think it's called linear approximation. Well, it is about linear approximation, but I'm not too sure what the book labels it as. So I think this is my first video in like a week or two, maybe. I don't know. So it's quite easy, arguably the easiest one in the chapter. In fact, I don't even think you need too much of an understanding of calculus to really get this one. So let's go over the historical context first, and the historical context would be that during the 1700s they didn't have a calculator to perform algebraic operations, so something like square root 3.98 is a little bit difficult to do. It's probably around 1.99 because 1.99 is close to 2 but not exactly 2 because 2 squared is 4. So when they would do like things like 3.99, they didn't really have a way to approximate it. Like square root 4, everyone knows that's just 2, such that you square both sides and 2 squared is equal to 4. But here they didn't really have something. I mean, I think from my memory, it's 1.9905. But again, that would be just super tedious. And they didn't really know how to use it. And I think it was primarily with the square root function. I know there are some other functions that are hard to calculate, like log of 99 or something, log base 99. So quite difficult, quite tedious. So they came up with linear approximation, which is quite smart. Um, so before we start, I'm gonna draw a graph here, and let's just draw a curve. I'm gonna think of a function to use, and I'm gonna think like a logarithmic function, only because this would be pretty applicable. In fact, actually, why don't I just use a square root x function, which I believe is a little bit um, more curvy than the logarithmic function, so it doesn't go flat pretty immediately. So let's take this graph and let's zoom in on that point right there, which is all what calculus is. I'm just zooming in on ordinary graphs. And yeah, it's pretty much calculus. As we zoom in, let's say that we take the derivative at this point, and then we find the slope of the tangent line, which is the derivative, same thing. But um, we define a linear line here. In other words, we're putting a line at this exact point. And let me just scroll up because I believe that's here. And we'll draw a line here. I'm not the best drawer, and my hand is not very good at being straight. So it probably looks something like that. Um, and let's just say that at this point, the derivative is going to be, well, we know that the function here is square root x. So the derivative of square root x is just going to be 1 over 2 square root x, such that it's 0.5. Yes, this is correct. So it's going to look something like this, where this is the slope, and plus plus the y-intercept. So it's going to be right here, and we're going to look here. In fact, we can apply this equation, and we can find another point on this line right here. And it looks pretty close to the actual square root x function here. So that's what linear approximation is. It's called using the linear line because we're assuming that the curve isn't deviating too much from that line. So that we can use this as a rough estimate of what it actually is, which is pretty genius because whoever didn't have calculators, I would have never figured this out. So that's pretty smart and pretty genius. So that's what linear approximation is, all summed up. So in other words, it's basically just finding the slope of the tangent line or defining a line at that point with the derivative at that point. And yeah, so before we get into, and actually, let me first define what linear approximation, or what the function is, which is f of x is equal to f of a plus f prime of a x minus a. Before we define this at all, or before I explain this at all, math is all about understanding why certain formulas work as opposed to just using them. If you were just going to use them, then you would have to memorize all the formulas, and that would be quite tedious. I mean, there's certain equations in math and science that you can't understand unless you get to really high stats, like Boltzmann's law. or sorry, um, like the Boltzmann equation, where you can't really memorize that. But this one is really simple calculus. So let's go over it real quick. So remember that the derivative of any function is this. The textbook doesn't go over this, so I had to kind of use some logic here. So actually, it should be the limit as x minus a approaches 0. So I guess it would be the same thing as limit as a approaches x. Pretty simple thing. So now all we can do is multiply x minus a on both sides. F prime a, x minus a, and then just add f of a. So that cancels out, and then you just add f of a to the other side. So that's how they get the linear approximation formula, where we can estimate f of x. Now, how does this work logically? Well, we know that f prime of a is the rate of change per unit x, and x minus a is delta x. So in other words, this would be delta y, delta x times delta x, and again, these just cancel out, giving delta y plus, I guess this would be considered the y-intercept here. So it's just lines again, and that would give you f of x. But notice that this only works as a is close to x. So when a deviates from x a little bit, that's when it gets a little tricky, and that's when linear approximation can't really be used. And note that linear approximation can be used for any function, regardless of its oscillation. So in other words, we can take a crazy, like that square root graph was pretty smooth and pretty symmetrical, or not symmetrical, it was pretty smooth and pretty predictable all throughout. But like once you get to damping or something, like something like this, which is actually real things that happens. That's called the damping factor. It's gonna look something like this, and it's unpredictable. So if you take the slope of the tangent line like right here, which will probably look something like that, you can only use linear approximation up to a certain interval. But linear approximation works anywhere. It's just that with curvier lines, a has to be really close to x for it to be an actual good approximation. Here it doesn't really matter that much. Like if a is right here, then this is pretty accurate, probably up until this point. Any further and it deviates quite a lot. So that's what linear approximation is in a nutshell. So let's do a practice problem. And to do so, we're going to do x squared. Let's say we want to find, or actually let's do square root x again. So square root x, what is square roots, let's just say 3.2, using linear approximation, which I'm not going to write out because that's kind of a lot. So first what we're going to do is we're going to take the derivative of this function, and we're going to define it for a, because remember the linear approximation formula is f of a plus f prime of a times x minus a. So the derivative of square root x is just going to be x 1/2, which is just going to be 1/2 x to the negative 1/2, which is just the same thing as 1/2 divided by 1 square root x, which is just going to be 1 over 2 square root x. But remember that it's f of a plus f prime of a times x minus a, which is just the same thing as f of a would just replace the x with the a. It's going to be square root a plus 1 over 2 square root a. So now what we can do is we can take an a that is really close to this value. So let's just take 3.33, which is actually not a perfect square. So actually let's take 4. Although I do know the value for square root 3, it's 1.73. But we're going to take the value square root 4. So you just choose one that's pretty close to here. This linear approximation is probably not going to be too accurate, but we'll see. So it's going to be square root 4 plus 1 over 2 square root 4, which is just the same thing as 2 plus 1 over 4, which is approximately 2.25. Oh, no, I forgot to, sorry, that's incorrect actually. Forgot to multiply by the x minus a factor. And x minus a is going to yield negative 0.8. So that was where I went wrong there. Because I was looking at it, I was like, there's no way it's higher than the original value, which is impossible, obviously, because 3.2 is behind 4. And square root x has a positive derivative all throughout. X is greater than 0. Yeah. So this is negative 4/5. So we can just rewrite this as 2 minus 1/5. Yes. 2 minus 1/5, which is equal to 1.8. So the value of 1.8 using linear approximation here is the square root of 3.2, which is quite accurate actually. I'm surprised because the square root of 3 is 1.73 obviously. So let me put this into my calculator and see what I get. Wow, 1.79. Pretty accurate here. So yeah, that's when we will use a linear approximation. But again, you can use it for any curve. Like you can take, um, let's say we can take like a, again, I used the idea of an oscillator, like harmonic oscillation. You can use it, well, because those are just cosine curves. Um, but I'm trying to think. Let me think of a crazy erratic function. Um, I don't know. So like let's just say that we have a crazy function here. Um, actually that does look kind of linear on some point. So let me like make it less linear. So if we take the derivative like right here, it's gonna look like that. It's gonna be really inaccurate at certain points. So here I would say that you can only apply it to within like this interval, which you can denote as whatever you want. So in other words, it will always work, but depending on the function, distance from x minus a will have a greater impact on what the linear approximation is. And that's all that is. So yeah, some 2.8 linear approximation.